We're going to talk about some important mathematical interpretations of this solution now. So to rewind a little bit, let's just talk about a first-order linear homogeneous DE. So that means the left-hand side is still the same, y prime plus py, but on the right-hand side there's a 0. We're going to do the same process. R of t is the integrating factor, and it's going to be exactly the same thing. The antiderivative of this term in the middle, right? That term talks to the problem. That determines the integrating factor. If I were to multiply both sides by that integrating factor, I will go ahead and follow the same process that I did earlier. 0 times anything is 0, but I'll just put it there for completeness. This is going to turn into y times the integrating factor, but it will be a perfect derivative of that. It'll be a 0. If I take an antiderivative, I will get this expression. And this will simply be a constant, right? If you differentiate a constant, you will get a 0. So that's why the antiderivative gives you that. And what I end up getting is c e to the minus p of t dt. I am going to call this the homogeneous solution. Now, that differential equation that I started with, the linear homogeneous one, I'm going to kind of come up with an abusive notation, and I'm going to say that you should just think of this thing as something linear, L. And next class we'll talk a lot more about what that is. This is what's called a linear operation. This linear operation is doing something to y, and at the end it has to give a 0. So this is why we call it the homogeneous solution. And here we'll just abbreviate it with YH. It'll be c e to the minus p of t dt. Now, there are infinitely many of them. This should sound a little familiar. From linear algebra, right? When you talk about ax equals 0, if you don't get a free variable, is if you have the trivial solution when x is equal to 0. So generally, you get something like this, right? And this is exactly the same thing that's happening here. You've got this part of your solution that just depends on the left-hand side. Just like this depends on the pivots in the matrix A. That's it. It only cares about that. Now, the non-homogeneous equation, the full meal deal, as they say, has the same left-hand side, but a different right-hand side. If we use the integrating factor, just like we did before, we end up with this, right? I'm just going to rewrite the solution. We will have c e to the minus p t dt integral, just like that, plus this antiderivative up there, and we will have that integrating factor on the inside, g of t dt. Now this is a mess. Please don't memorize this. Just like before, this is our homogeneous solution. It came back, right? This thing is what we will call our particular solution. This thing only cares about p of t. It only cares about the left-hand side of the differential equation. Now, this thing over here requires info about the right-hand side of the differential equation, right? This part of the solution is there to deal with the right-hand side. So you should think of linear algebra where you've got ax equals b. Your solution, part of it comes from the homogeneous part, the pivots. The other part comes from dealing with the right-hand side, the particular solution. And that's exactly the same thing that's happening here. Y of t is going to be made up of a homogeneous part and a particular part. This part comes from dealing with the left-hand side. This part comes from dealing with the right-hand side. What we're going to find is that there are many, many parallels between differential equations and linear algebra. Differential equations, when you're talking about linear equations, they just end up being an application of linear algebra. But it takes a little bit of work to get there, so I'm going to talk about that as we keep going throughout the semester.